Here I have chosen a beam to validate and to show the step. Now, this is the agenda, is the content, this is the flow, how I will try to explain that what is my project is. First, a small introduction overview that how this problem came into people's picture, that how it should be solved. Then the problem statement regarding to my problem. Then a small mathematical formulation or framework for the project. And then I have done some simulation and experiments to validate this mathematical formulation, after that inference and the application of my step. Before starting the main project, let me give you a little history, a little overview introduction. You can see there is this photo. This photo is a particular shape, this is known as Liberty. This photo was captured in 1943 December when Second World War was ongoing. The main reason of the hull cracking of the ship is vibration, dynamic loading. Now, how this thing happened that initially these ships or aircraft, they are generally riveted junctions are preferred, but due to the shortage of labor, they welded the entire hull. Now, North Atlantic in December there is a very harsh condition, and along with the dynamic loading, the cracking of the hull, the defect that propagated the it accelerated rapidly, resulting in this phenomenon. This came into picture in this year. After that, there is a benchmark shift happened in structural dynamics and fracture mechanics. In 1921, Griffith proposed his idea of critical energy theorem, which is that for any material there is a critical energy. If you supply energy more than that critical energy, a crack should propagate. And there were no assumptions or nothing like that. Looking at this phenomena, we have to shift it from that theory, because dynamic loading can cause this kind of devastating failure. This was the first example of that. Now, if we look at this table, for the aircraft components, look at the percentage of failure. This 55, highest among all of them. That percentage of components which fails under fatigue loading. Fatigue is essentially, it is a dynamic loading. So, this is the reason why I have chosen this project, the motivation of that is. Now, let's come to the problem statement. The problem statement is to investigate, to find out a relationship between first notch depth and the frequency shift of a beam, and notch location and the frequency shift. And the second part of the project is to find out the residual life of damaged beam under the loading condition is vibration loading. Now, I have for experiment, you can see there are three bidirectional fibers, bidirectional composite fiber samples are there. So, at the end of this experiment,
can you put the figure horizontally?
Yes.
Yes. So we can just rearrange.
I will just put
so that while looking the thing there, if you put horizontally, the sum minus 45 will be easily readable.
Okay. Sure. So at the end of this presentation, I will one of the inferences, which fiber orientation is most suitable to arrest this crack, to increase the residual life of the structure. Now, the mathematical starting of the mathematical formulation starts with some assumptions that how I will model the beam. I have chosen an Euler-Bernoulli beam with the dimension of LVD and notch depth A. Now, notch depth have varied between 0.1 to 0.3 due to certain reasons. There are generally two reasons. First one is the fracture mechanics validity. Now, what do I mean by fracture mechanics validity? The fracture mechanics has two parts generally. I have used LEF, linear elastic fracture mechanics. Now, linear elastic fracture mechanics has two main assumptions which is significant here. First one is small scale yielding assumptions. Now, the thing is, if we go less than 0.1 notch depth by beam depth ratio 0.1, it will produce insignificant effect in the beam's mechanical behavior. I mean, it looks like that almost the notch is non-existent. And again, simultaneously, if we go beyond point 3, the problem is the beam will behave like two separate segments. The plastic region, when we apply load, the plastic region will be so prominent that we will not be able to apply linear elastic fracture mechanics phenomena. One of the major assumption is Hooke's law. It will not be applicable in that region. So the notch depth is constrained in this region. And the second thing is stress intensity factor. Stress intensity factor generally works in this range only. When we are talking about linear elastic fracture mechanics, stress intensity factor is concept is valid in this region, in this framework only. If we shift to elastomeric concepts or viscoplastic materials or viscoelastic materials, there is no such concept of stress intensity factor because they will talk about strain rates, not strains. So these are the assumptions I have taken. Now the material properties are listed here. These are given from the manufacturer's end, the volume fraction and parameters for fiber and matrix. These are there. This is fiber and these are fiber and resin these are properties. Fiber is taken as bidirectional threaded GSM, woven in both directions. And
you know how he has fabricated the procedure?
It's a diamond cut sample.
How he has fabricated this?
Hand layup.
That I know.
Hand layup plus minus 45 or 0.40 the configuration. Hand layup, and after that diamond cut. Samples of it.
And also you should tell that how the uniformity of the beams have been maintained. A common plate has been made and
60 by 60 a common plate was
and that you have to mention so that whatever the errors are there, it has been taken care of.
Okay.
So tell a little bit about the fabrication.
Okay, the fabrication is generally there was a big frame was there. It was 60 by 60 frame is there. 60
so that one you can tell when you are showing that before that. The samples are there, no? That itself you tell that okay, these are all the samples.
Okay, these are the samples which are manufactured by from one single plate. The 60 by 60 centimeter by 60 centimeter one plate was there. The after construction of the entire plate, which was used by hand layup methods, one layer of resin, then fibers were aligned, then again the second layer. This is how the layers were stacked. Then using hydraulic press, they pressed it, after the autoclave it. Now the plate is complete. Now with the diamond cutter, they cut it with 60 centimeter by 60 centimeter by 40 mm and 3 mm is depth. These samples were prepared just to maintain the uniformity and now to analyze a composite material there are several ways. One of the ways, if you want to predict the nature is Faraday. It's a very accurate method to discretize the beam with different areas where you can assign properties. But I have not chosen that method because when I was doing this project, one thing I kept in mind that my outcome should be easily, people can easily implement it. It should not be very much complex. See, applying finite element in a beam or in a large structure, it will give you very accurate result, but simultaneously it includes a very, very costly numerical analysis. So what I have done that initially what we used to do is we used to homogenize the material. We find out the effective properties of a material of this beam, which is 10 layers of laminas are there which are compressed. So it is basically an orthotropic configuration. Orthotropic configuration should have 9 independent material constants. 3 Young's modulus, 3 shear modulus, 3 Poisson's ratio. It should be there. Now there are several ways to homogenize that. One is Morita method, the others are Alpine criteria is there, rule of mixture is there. since it is a bidirectional fiber, I have chosen Mori-Tanaka just to take care of the directional effects in the fiber. Now, to start the Mori-Tanaka method itself has some assumptions. What is assumes that the entire matrix that is homogeneous isotropic, the basic solid mechanics assumption, homogeneous and isotropic. Now the interface between two layers, I mentioned that there are 10 layers. Now between two layers there is a adhesive. We do not consider the adhesive as a separate material. It doesn't affect the overall mechanical behavior of the sample. It will not affect. It is in the continuous phase of the matrix. The third one is the entire structure, the matrix and the fiber will obey Hooke's law. And the fourth one is there should not be any shape effect. I mean, of course there should be, there will be any shape effect, but it should not affect the mechanical properties. Like in basic solid, in solid mechanics, what I assume that plane section remains plane before and after bending. This is the same assumption we are taking here. That elongation of fiber, when we elongate a fiber, the cross section should decrease, but there should not be any effect of this on the mechanical properties. Now, according to Mori-Tanaka theory and Wettstein reformation, they said that stresses and strains in both matrix and fiber, they are correlated. How they are correlated? They are correlated by two tensors. One is Tij and another is Aij. This Aij is Mori-Tanaka tensor. Tij is given by this formulation, where Lik is Eshelby's tensor. Now let's talk a little bit about Eshelby's tensor. Eshelby's tensor is the heart of this entire formulation. What Eshelby's tensor says, this is a general method of general format of Eshelby's tensor. I have made a mistake here. It should be Lijkl, because Eshelby's tensor is a fourth order elasticity tensor, just like Cijkl. What we use in generalized use of sigma equal to C into epsilon, just like C, we have Eshelby's tensor here. What Eshelby's tensor correlates, basically all the elements of Eshelby's tensors are functions of Poisson's ratios, like this. Like this one, I have given an example, L2211 and 3311. This is an example for what Poisson's ratio tells us. Poisson's ratio correlates the strains of two directions. What is the definition of Poisson's ratio? It is minus of lateral strain by longitudinal strain. In a similar manner, when you have 9 independent constants in 3 directions, you need to find a way to correlate all the 3 dimensions. This Eshelby's tensor does the same thing. What Eshelby's tensor says, that imagine there is an inclusion in the form of a fiber in an infinite resin matrix, in an infinite matrix. Now it is similar to the Kirsch problem we solve, or a shrunk fit problem which is solved in solid mechanics, where you apply stress in one direction and there is a hole in the plate. It is a sort of the same problem. By this method, we find out Lijkl. This we will be able to find out this matrix. There are formulas are given, all of that as mentioned here. So, is it after this? This is basically a step. I mean, it's basically a mechanical process to follow, where we will put all the values of mu n. We know other properties of independent properties of matrix and fiber. We know. We just plug into the values in these equations, and we will be able to know the effective properties. Now, what Mori-Tanaka method gives us? It gives us 5 independent constants of one laminate, for particular one laminate, one layer. But my beam is constructed with 10 layers. Now, how I will go from 5 to 9. This is the complete framework. How I will get E1, E2, G12, G23, and U12. These are the 5 independent constants which Mori-Tanaka method will give us. Now, from there, I have given a sample calculation for only plus minus fibers. The rest of them are similar. for 0.45.
GP make it capital.
Sorry.
GPA.
Okay.
Small case, no? That is.
G should be capital.
G should be capital.
Okay. Now generally what happens that in the depth in the z directions x, y and z in the z direction we have taken that E3 equal to E1, G12 equal to G13, and this approximation I have taken for the sake of simplicity of this calculations. The damping properties, since it's a dynamic loading problem, the damping property of the beams are found at the logarithm. Now we have found 9 constants. We have the damping value also there. Now let's proceed to the second part, where we are applying the load, finding out the eigenvalues, which will give us the natural frequencies. Now this is the fourth order eigenvalue equation, considering the dynamic loading. This will give us the natural frequencies. First 5. I have considered only first 5 natural frequencies with a focus on higher modes. Now why higher mode I have focused? That if you look at the cracks, what is the influence of a crack in a structure? Cracks induce local deformation, they induce local problems in a structure. Now vibration is a global phenomenon. If we look at the lower modes, let me show you some pictures. This is the second mode. You can see the mass distribution or the geometric complexity of this mode shape is not very much compared to, look at the fifth mode. Compared to this is the fifth mode. This is the only twisting mode among first 5 mode shapes. Look at the complexity of this structure, of this mode shape. Any crack or any defect situated here or here will have a devastating effect on this mode shape, on this structure. So any change in the natural frequency due to any crack or any defect, any impurity, it will be more prominent in the higher modes due to the complexity of the modes. That's why there was a higher focus on the higher mode shapes.
Generally, is it always happening in higher mode shapes are complexer?
Higher modes, geometry of
Depends on the width and thickness.
Okay.
Width is more and more, it will be like a plate.
So
it will become like a plate, and then bending and torsion modes will start coming.
Okay. Because of that, the shape will start forming.
Now, the second part, residual life calculation. Let me give you a small idea that how I calculate residual life, because generally what happens that vibration loading essentially gives to fatigue phenomenon at the end of after some time. Now the problem with fatigue is there is no solid mathematical framework to analysis of fatigue loading. I mean, in microscopic level, obviously you can analyze fatigue loading. For example, you can take an element dV with the 2 5 directions, you assign the properties, matrix and fibers separately. Now you do numerically integrate it to find out the fatigue loading or the residual life. But the problem with that is you cannot apply the same theory on a larger scale, for a larger structure, for a beam or for a column or for a plate. This is problematic, because what happens that to propagate a fatigue loading or to fail a structure in fatigue, you need one crack, particularly one crack which should be propagated rapidly and then it will fail. That should be there. Now for composites, I have, since it's a composite structure, what I have done that I have created a notch. After that, I created a crack with 3-point bending load, so that the primary mode of failure becomes delamination. I have done it deliberately because I should have a control over the type of crack forming, because if there is multiple cracks, then it will be very difficult to predict that for which crack is the structure is failing. So a 3-point bending test was done of the displacement control 2 mm per minute. 75% of yield stress was applied to form the crack. Now, for mathematical framework, the same equation with the dynamic loading is applied. Now, dynamic loading scheme is omega is our second mode natural frequency. This is the omega. How I will calculate the f? Now, f was calculated in this manner that my loading was given by a shaker, electrodynamic shaker. Now, as per